Thank you for coming along, everyone. Okay, so I'm Stewart. I'm from an organisation called the Cambridge Crystallographic Data Centre, which is a non-profit organisation. I'll tell you a little bit more about that in a slide or two. And there's a thing called the CSD, which is essentially a database of chemical structures. I'll tell you about that in a few slides as well. My involvement in this project was last November we released version 1.0. I was the Scrum product owner for that phase of development. I'm actually a software developer really. Okay, Cambridge Crystallographic Data Centre. We're kind of a spin-off from Cambridge University's chemistry department, and we are dedicated to promoting crystallography and chemistry. So the way we do that in practice is we maintain a thing, you see the symbol lots, it's a symbol for the CSD, Cambridge Structural Database. As an organisation, depending on how you count us, there's about 70 people, of which nearly all of us are based in Cambridge, there's a few over in North America. And we do several different things. We are a fully fledged research institute, so we have scientists doing real proper research. We're also a software vendor. One of the key purposes of this software, aside from adding value to the data that we're providing to people and making it more valuable, making it more useful, letting people analyse their own data, is we sell a lot of that software, and the money we make from that funds the curation of the structural database. CSD 50 last year was a fairly momentous date in the history of the CSD, being 50 years old, which for a database is quite old. We think we're the oldest numerical database that's still actively maintained. Problem with being 50 years old is, of course, we predate things like sequels. That's kind of coloured art at that moment. Okay, so what's our purpose? What do we do? Lots of people come up with experimental data. So these are crystals. You can bombard these crystals with X-rays or neutron beams, and this causes funny diffraction patterns, which you can measure. These are really clever maths, and you ultimately work out what the chemical structure is within those crystals. That's happening all the time, all over the world, and the data is either published in peer-reviewed journals, and it also gets submitted to us, and then we make it available to the world. So if anyone wants a organic or organometallic crystal structure at the molecular level, they know they just come to us, and we're bound to have it. This data is then useful. We can derive various pieces of knowledge or pieces of information from it, which supports a variety of analysis, which our software deals with, but you could use your own software instead. So CSD, thing that we were, our purpose, essentially, it has lots of things like this. This is just a schematic of obviously 500,000 structures we added 7 years ago. So this data contains every single published crystal structure in the scientific literature. Historically, that would have been manually extracted and put into the database. Nowadays, it's mostly automated. We get direct feeds from the publishers, for example. In addition to the published structures, lots of crystallographers send us the data directly to make available. And more recently, we've started extracting data from patents as well and other sources of information. The important thing about this is manually curated, so that we are confident in the quality of the data. Scientific publications have typos in them, for example. That sort of thing will be corrected at the point of entry. These I guess, highly trained structural chemists who do the creation can also add additional data that may or may not be in the original publication. One example is something I'll talk about briefly later on, which is melting points, for example. So the temperature at which the crystal melts is quite often measured as part of the experimental process. That data is also put into the database. And there's links to other external data sources. This graph shows how the database has grown in terms of the number of entries. Starting at, well, it's almost an exponential growth. That number at the top is about a month old. We've surpassed 850,000 structures. And it's kind of interesting. All of this data, depending on how we store it, sort of 5 to 8 gigabytes, so not all that large actually. And the numbers of entries we're talking about here, 850, it's not really big data by today's standards. But in this phase of our growth, it was big data. There were database formats which could comfortably handle that kind of data and do the type of queries that we were handling. Certainly in the 80s, disk space was a limitation for when we were distributing the database, which has consequences on the way we store data even now. For example, a lot of the data is packed into integers, so multiple values packed into a single integer, which is horrendous to work out what that data on the disk means. And why would you do that? That's just because in the 80s we had to care about every single byte. Already in those times were substantial amounts of data. Okay, so that's where we're starting from, and I'm here today talking about CSD Python API. So what I'm hoping to discuss is briefly what our motivations were for producing the API, and why we went ahead and did it. And then, while we were implementing it, we learned a lot as we went along. So some of the lessons that we've taken, I've pulled out, I've got little mini case studies and stories about those, and I'll try and explain what we learned. So maybe you guys can take those lessons, and maybe your feedback for us. Okay, so a few years back, we asked, or the organisation asked these questions essentially. How can we make the data more accessible? More people use it, more widely available, available to people from other domains maybe. And how could we make the data more useful? How could we supplement it or provide additional analyses from it, include other information within it? And we also had this sort of the internal question. We've got, as you imagine, for an organisation of our age, we've got a lot of historical code. We do still have Fortran in production. I fixed the bug about 3 weeks ago, which was entered into our bug tracking system 13 years before. And software engineering has developed over that time quite substantially. So what was good software 10 years ago perhaps wouldn't be considered good software now, with different attitudes about unit tests, for example. So it's fair to say there's a certain legacy here. So no, perhaps the scripted interface is the solution to these questions. In terms of what advantages the user might see, we provide desktop software to do a lot of analyses, and the desktop applications are very well suited to doing very specific analyses. However, that can be graphical, pointy-clicky processes, which are great if you want to do it once or twice, maybe a few tens of structures. When you're talking about hundreds of structures or thousands of structures, or even 350,000 structures, it's not the process isn't going to be up to the user's needs anymore. So script it, automate it, we can talk about next. Also, because the desktop applications, we sell them, so they're not open source, if a new killer feature is required, maybe a new method is presented in the literature that would be really useful for our users, there's a very long cycle between us trying out methods, seeing if it's working, putting it in software, and then releasing it to people. So maybe this is a way of getting new science out to people quicker. We also have most crystallographers are very into publishing their data. They have to do that in order to get the grants in order to carry on doing crystallography. And so they'll generally have analyses based on their data. They'll want to publish that data, but they perhaps also want to share the analyses with their colleagues, and this will provide them a mechanism for doing that in a way which there's someone else to reproduce the study of the science. And lots of users use many packages which are pre-existing, and they'd like to use our stuff at the same time, or alongside all of these other tools. So at this point, Python is going to be obvious. Okay, I've skipped about one key thing that a user might be interested in, that's accessing the data. So searching for a particular crystal structure, might be, or a substructure. Historically, so we're talking early 70s maybe, we actually distributed the CSD in book form. So we were responsible for typesetting the books, printing them, and then be sent off to various university libraries around the world. And if you wanted to do a text search, so let's say I wanted to find all the structures with this name, I would hope it's in the index, go and look at the index, and find the structures I was interested in. If I was interested in the chemical structure, though, it was even worse than that. It's not very easy to index in a general way chemical structures. So it requires someone to actually flick through the pages and look at the 2D diagrams of all the molecules. Kind of solved that late 70s, 80s with a software package that's running on a graphics workstation. I learned about that when I was at university doing a chemistry degree, which is in Fortran. That's replaced in slightly more modern times. In 2002, it was replaced by a program called Conquest, which was actually written in Python 1.5. It's got an interface written with TK, and that software hasn't really changed since. So it looks like an ancient interface. It's only now, 15 years later, 14 years later, that the science has been beginning to be surpassed. Ruth has a visualization software, which we'll talk about in a second. Welcome to 2016. We're now all fond of web interfaces. We did eventually move to a web front end. And here we now move into Python. So in terms of usability, so the user looking for structures gone from books through software, which is great for doing specific things that software is suited for, but now Python kind of empowers the end user to come up with a solution to what they actually want rather than what they thought they wanted. I'm reusing this slide from 2014. So when we were sort of in the early stage of the API, and we were promising to essentially a user group forum, and what we were developing currently, we're saying that next year we're going to introduce these new APIs. So it's a Python API and a RESTful web API, and then you're talking about Python one here. So these are the key things that we said it would enable. We're mostly satisfied that. Just read it out. So it allows analyses that weren't possible through our existing interfaces, perhaps because we hadn't thought about them, perhaps because a 2020 approach is not really suitable for the analysis. Integrate much better with third-party applications, and it allows people to share their analyses alongside sharing data. So in terms of the software, this is kind of how it's built up. This is representing the CSD database, and we've got a huge set of C++ code. It's 4.1 million lines of C++. Not all of that's used in production, but it's a substantial amount, which has a huge learning curve. So we've got a nice friendly API, and people can access the useful bits in a nice friendly way. And then on top of that, we've built integration mechanisms to other tools, whether they be internal or external. This part now, though, is largely hidden from the user. So you're writing a Python script, you don't need to care what's happening here. So in normal use, that would be the CSD, which is stored in our proprietary data format. As we're migrating that now to SQL, it's in 1970 anymore, we can do that. The user won't need to alter their scripts when we ship out the SQL version to them. You can also access other industry standard file formats and data. And the user writing the scripts doesn't need to care about that and differences as well. Just a little example. So this is an IPython notebook example. Just got this up here just to explain the structure of the API slightly. So there are a few sub-modules that do particular things. We have 9 of them in total. It's called I/O, and surprisingly that deals with all the I/O related magic. So this is a way we open essentially a connection to the database, and this is what you do for just the CSD. This bit here would change a little bit if you're accessing a different data source. After that, everything's identical. I don't think you normally access in terms of indexes, but like a simple example, just getting the first entry, and each entry has an identifier, which is right up there. That's it. That's an arbitrary 6-digit code. All of the data is accessible in terms of entries, so that's essentially one piece or one set of data about a crystal solution, and that will contain in it crystal, which is all the crystal data, so what the cell dimensions were, various crystal graphic properties, and then crystal will contain one or more molecules that coordinates. In my example here, I'm just creating a diagram. Like, it doesn't mean anything. Okay. The main value of the talk now, though, is me describing the lessons of Okay, so various lessons. I don't literally mean we learned there's not any single user. What I mean there is can't treat all users as equal. There's different classes of user, and that's quite important. It's kind of a mistake we made. We thought we've got this one prototypical user described by a persona, satisfy them, everything's going to be great. That's not true at all. We have very distinct classes of users using the API in very distinct ways. Integration opportunities, this is a good surprise, far beyond what I expected, and that's mostly a benefit from the Python ecosystem. I really appreciated to start with. Most of those I'm now going to discuss in case studies. Okay, so the first one is that scientists are no longer limited by what we think they should do. About empowering them. So this is great for a user who wants to experiment with the data, or experiment with our scientific methods we're providing to them. They can prototype things using this tool as the back end of the underlying system. And it's also great for what's called large-scale analysis, so looking at all of the data in the database, doing those statistical analyses to find average properties, those type of things. They can lock themselves out and do what they like. It's great. One particular quote here, so this is a real quote from one of our PhD students, is at the end of their first year we released the API, and a few weeks later they said, I was doing this particular study, and every time I wanted to do it, it took 6 weeks of my time. Python API, good morning. So the value in their thesis now as a result of them getting 30 odd times more stuff done is huge. There is a downside. Okay, this slide was presented at a crystallography conference a couple of weeks ago by one of our scientists, and they wrote a script, I'll show you in a second, to produce this data. So all this data is doing is showing you what the largest entries in the database was. Perhaps very pretty molecules, but they're molecules that people might be interested in. The script that they wrote with no developer support was this. This is not how I would write the script. It's a fairly ugly script. It definitely isn't the most efficient script. But that's not the point. The point is a non-developer was able to put together a script without any assistance. Essentially what the script does is it iterates through the whole database, picking out the entries that they are particularly interested in, and at the end it spits out the largest one they found. They could have just done that by running a search with some filters and then doing a sort on the search results, and bingo, the result. I think they said this took 7 hours to run. Way I just described would be seconds. They were able to do that and got what they wanted. Here's the downside though. 999 atoms. That's a funny number to have as the largest entry. Seems a bit coincidental. Actually, the database format being used there had a limitation. It can only store 999 atoms. So since I guess we as developers are responsible for communicating those caveats and those limitations. Let's skip on this one at a time. Okay, this is another case study which huge value. We are assessed based on the quality of our data. Our data needs to be high quality. We also have quite a lot of data which people might not associate with CSD. One of the things there is the melting point, so the melting temperature of the crystal that was used to get the structural solution. More than 60,000 of our entries have this melting point data collected over this span of the history of the CSD. That's a huge source of value which is unused. We haven't been making it very easy for people to get to it. We should. The API gives easy access to it. Unfortunately, essentially, it's almost cut and pasted out of subsequent publications. So it's stored in the form at 70 to 75 degrees C. My personal favourite was explodes at 68 degrees. So some of them are not actually melting points. And so lots of ranges, lots of things, so close to 200 degrees C. There's loads of off by 273.16 areas. So I'm wondering if anyone can work out where they're coming from. Yeah, so mistakes in transcribing what the units were, essentially. There was over 400 entries, which were off by 273.6 degrees. So we were able to write a quick script which found dubious entries if the melting point was lower than the experimental temperature. Probably wrong. If the melting point is outside the ranges of experimental feasibility, probably wrong. And then we could correct those. We could also compare with other third-party sources, and if we didn't prove them, it might be because we have a different crystal structure, it might be one of us are wrong. so we were able to get permission for someone to look at the manual and get back to the original paper if necessary. And so, as of the last release, it's great. The next thing is value in what we put together without realising how valuable it was. So we put together, so we've got a tool called Mercury, it's a visualisation tool, and as a way of customising Mercury and letting people add their own features into Mercury, we have a script menu which runs the API. And as a demo of that, we made a little report generation. So the user puts a molecule of interest in the visualizer, they click on the button to get the report, and that spits basic crystallographic data. We thought, oh, wonderful demo. Users picked up on this and said, hang on, we can use this for our internal report generation purposes. They create crystal structure in their company, and they have to write a report in their notebooks or pass it to other teams. So we rewrote essentially the templating for the report using Ginger 2, and actually for this release replacing that with a way of producing Word documents. And that's hugely valuable. So I guess the key here is when you show a new feature to your users, demoing it, listen to their feedback, perhaps they're more excited than just from them. I'll just finish off on this one. This is something we got kind of wrong, we've corrected now. As I was saying before, we thought there was one user. That's not true. In early versions, we provided it to what we call friendly users. These are Python users. And we provided it for the pip package. We thought that'd be no trouble. And lo and behold, didn't have any complaints about that. Next version along, which went to everyone who wanted it. We had conda support, so lots of things. We reduced some of the pain, and then suddenly with all of these complaints, hundreds of complaints, 5 different types of complaints, we kind of, they're all sort of user errors, it's not something we've done wrong. We can improve those through improving the documentation. So we did that, same complaints again. We realised, well, actually, a lot of people using this aren't Python managers, they're not programmers, so they're just doing this because they want to get a job done, they don't understand. And so so this current release, and there's an Anaconda guy in the audience, we're relying on Anaconda quite heavily, and we're just installing a version of Python for users, and they don't have to care about installation, they don't have to care about thank you. That's the end. That's a paper about CSD. If you want to learn more about the CSD and the history, and if you want to look at the API itself, there's a link to the documentation, which you can find everything from that.
Probably got time for one question. Yeah.
Sorry if I missed it, but what was the one thing that reduced that PhD students' turnaround time from six weeks to?
Yeah, so they had to do it manually through the graphical user interface. And every single structure they had to repeat the process manually. And then the results coming out, they had to do some analysis on it, which took some time, which they could have scripted, but they didn't have the underlying facility to do the scripting. The analysis was in the API itself, so it was just a simple function. So simply they could script out the equivalent of clicking and searching, and then the analysis was already coded up with a simple small script. After a few hours.
Lovely. Thank you very much.
Thank you for your time.